those series are designed to promote excellence in the casework engineering, and they are featuring distinguished speakers. The first one in the series with Professor Ian. That seminar was hosted by Micromachining Science, and it had Professor Ian as the speaker. We are very pleased that Professor Heuer from Material Science and Engineering accepted to be the second speaker in that series. And also we are very grateful to the Electrical Engineering and Computer Science Department, which is hosting that seminar. And I would like to introduce Professor Meral Bozoyoglu, the chair of the EECS department, who is going to introduce our distinguished speakers.
Thank you, Aka. Actually, it's an honor for me to introduce Art Heuer, and we all know that he doesn't need an introduction. Everybody knows Art on campus. But he has been an assistant professor at Case since 1967, and he's a Coursera professor of ceramics since 1985. Actually, Art has his PhD in ceramics in 1966 from the University of Leeds in Vancouver. And he's world renowned for his research accomplishments in ceramics area, with more than 500 publications and more than 30 PhD students and 40 PhD master students. This may be more now. And actually, Art received the first gold award, actually, from the Ceramics American Society of Metals in 1997. And he's also a National Academy of Engineering member since 1990, and also a winner of Heuer Prize last year. And there are many more accomplishments to this, but here's actually golden ceramist Art Heuer, as his alma mater calls him. Thank you.
Well, thank you, Anika, for asking me to give the second lecture. I think it's a wonderful idea because very often one is well known around the world, but not to one's colleagues. So this is a really lovely opportunity for me to tell you about something I've been working on for about 12 or 14 years. And it seems to me an appropriate topic for the topic I've chosen is appropriate for this kind of hopefully wide-ranging audience. Material science of silicon MEMS is the obvious title. A two-way street refers to the fact that I think material scientists can and have made significant contributions to the field of MEMS, and I'll try to show that. And conversely, MEMS enables a class of experiments which are very useful, but which would be difficult or impossible to achieve with macro specimens, and I'll try to show you that as well. I want to acknowledge people here at Case I've worked with, particularly Hal Kahn, a research professor in my department, who has worked with me on everything that I've done in this field, and I'll tell you about today. We had very nice collaboration with Roberto Ballerini and Bob Mullen in civil engineering. The asterisk indicates that Roberto, many of you know, has moved on to the University of Minnesota, but we had a wonderful collaboration in applied mechanics, and with Bob Mullen, where some finite element work. Joe Perry in my department has collaborated with us on some aspects of galvanic corrosion, which turned out to be important and interesting in MEMS processing. And I have to make a special debt to Miran Maragani. He and I have not ever worked on silicon together. We've published on silicon carbide, but it's clearly he who introduced me to the field of MEMS, got me interested, and the rest I'll try to show you about this afternoon. Well, one can't give a general MEMS talk without a motherhood slide, and this is the motherhood slide that I've chosen. Oh, I'm not sure why that happened, but of course, all silicon chips provide electronics, if you will. The brains of any device here is the attempt to get some other sensors involved and to perceive and control the environment. Sensors and actuators are obvious, and I'm going to show you examples of some particularly successful MEMS sensors and actuators just to show you that there is some reality here. Mechanisms is a special jargon word, if you will. A mechanism to a MEMS person is like a fulcrum or a lever. It's not the mechanisms that we in other fields we use to describe reactions or theories or things of this sort. Okay, well, here are perhaps two of the more successful MEMS actuators. I think the projector we're using today almost certainly will have this digital mirror device made by Texas Instruments. It's interesting, the person who pioneered this at Texas Instruments was a Case grad from our physics department. I've been told many times by TI people that if they'd have known how much it would have cost to develop this device, they probably would not have embarked upon the development. It's now successful and they're making a profit, but estimates run that it costs between $500 million and $1 billion development costs to develop this bit of hardware. It's just fits on a chip. In terms of numbers, probably inkjet printers are probably the largest number of MEMS actuators around, and I'm sure most people in this room would have made advantage of that today. In terms of sensors, I've gotten two examples. Pressure sensors, they're probably the oldest MEMS device. The first MEMS device that became commercial, they're generally simple. There are various versions, but generally as a membrane, you measure capacitance changes, a very typical way. And all of you who drove to campus today would have had an accelerometer in your car to activate the airbag if you should get into an accident. There's an active deceleration. It works by having a fixed and a movable mass, and the motion of one against the other will generate a voltage, electrostatic actuation. And I'll show this, first of all, because it's incredibly important. The previous generations of accelerometers, which were used in the early days to activate airbags, were expensive and could only be available in the most expensive cars. It's when these at prices of $5 or $10 became on the market that they became standard in every automobile made. And this must have occurred about 10 years ago. I show this, I go a little detail because we're going to use the same type of electrostatic actuation in some of the MEMS devices we have fabricated. Okay, so this is what I want to tell you about today. Residual stresses, LPCVD is an acronym for low pressure chemical vapor deposition. It's the workhorse tool to make polysilicon. Polysilicon is what MEMS types or electronicers will talk about, something that we in material science would call polycrystalline silicon, but the word poly or polysilicon has become so widely used, maybe you all know about it. These are sometimes really nasty because residual stresses per se aren't bad, but residual stress gradients can be awful and can turn computer chips into something that looks like potato chips. And so we had to deal with that. However, we found that we can make use of these residual stresses to allow on-chip mechanical testing, and I think that's a really neat development. We discovered in the last few years, this is the work that Joe Payer and I did, that there can be galvanic corrosion occurring during MEMS processing, and I don't believe the electrical engineers, knew what galvanic corrosion was really in the way material scientists know, and realized the detriments in a very standard MEMS processing technique. Okay, these are things I think we have helped the MEMS community. On the other hand, we've made devices which allowed us to study high cycle fatigue, and we've discovered things that would not be, we would not have been able to discover using conventional types of specimens. And we've been able to use MEMS devices to study oxidation-induced stresses of silicon itself, and some surprising results on the viscosity of SiO2. So that's my outline. I hope I can get through everything in a reasonable time. There are two types of so-called micromachining. This is, again, a jargon word. This is either, as shown here, surface micromachining, which is an additive technique in that the silicon wafer is just a substrate on which supports the device. Bulk micromachining would be is a subtractive technique. You take a silicon wafer and etch away in selective ways. I won't talk at all about bulk micromachining. All the work we've done has been surface micromachining using the class 100 MFL just about 100 yards from here. But techniques, our devices have all been very simple, so-called single mask devices. We take a silicon wafer, we oxidize it, thermal oxidation to make a sacrificial oxide. Then this is the working bits of the unit. It's the, in this case, LPCVD of polysilicon. I'll tell you more about that in a moment. And then we put down about a micron of CVD, silicon plasma enhanced CVD now, and use this as a masking oxide. And we have conventional photolithography and plasma etching, both for the SiO2 and the silicon. And then this would be a cross-section of some device. Is a time you use HF dissolution to remove the sacrificial oxide, and you depend on time release such that certain small scale features are floating and larger scale features are fixed, and this allows you to do all sorts of really clever device fabrication. Ours have been simple, but there's a degree of cleverness that I think we can claim. Well, microstructures are something that material scientists generally think a lot about, and certainly much of my own research career over the years has been involved with thinking about structure property relations in materials, and polysilicon made for MEMS is no different. If you ever have occasion to work in the MFL, you can do anything you want as long as it's something they've done before. And that's fairly typical of any fab. They have very strict rules about what you can and cannot do. Any of you who go in the fab will know what I mean. And our CVD reactor works in this temperature range of 540 to 620. And you can pick any temperature you like in that range, but not much else outside it. The reaction we use is just the cracking of silane under these conditions. And it's inevitable and well known that films that are deposited under these conditions come down with residual stresses. These are growth or intrinsic stresses. Since there's not any real thermal expansion mismatch stresses. And it's curious that at the low temperature end of the regime and at the high temperature end of the regime, the stresses are compressive and of significant magnitude, a few hundred megapascals. But in the intermediate temperature regime, the stresses are also significant, but opposite in sign, they're tensile. And it's relatively straightforward to understand the origin of these stresses. At the lowest temperature regime, this is an electron micrograph. Each of these films are 5 microns in thickness, deposited at different times at these temperatures to give the same thickness. But the idea is that, and you can see it particularly clearly in this sample, this is the SiO2 sacrificial oxide on which the silicon is deposited. And the kinetics of deposition are just a tad faster than the kinetics of crystallization. I'll come back, it's an important point. It turned so that by the time you grow 5 microns of amorphous silicon, the first form material begins to crystallize. It's just a kinetic effect, and for the number, if you make a thinner film, you could get a purely amorphous material. You can see this at 570, where under the same the growth conditions to allow a 5 micron film to be formed, about 80 or 90% of the film has crystallized. And by the time you get to 615, crystallization is essentially instantaneous. There is no or very small amorphous region, and you get a very familiar columnar microstructure. Very many CVD deposition processes give rise in columnar microstructures. Essentially, you limit nucleation, and whatever nucleates early just continues to grow. Now, the origin of these tensile stresses is easiest to understand. It arises because there's a small density difference between crystalline and amorphous silicon. Amorphous silicon is less dense than crystalline silicon. So when the material crystallizes, the structure would like to shrink, but it can't. It's essentially fixed. There's no material is essentially doesn't support any plastic deformation at these temperatures, and the result is a tensile stress of significant magnitude. At lower temperatures or at higher temperatures, the stress origin is different. It's almost, and not as well understood. It's almost certainly a consequence of a non-equilibrium interstitial population. Whether it's interstitial silicons or interstitial hydrogens, we don't know, but if you avoid these tensile stresses, then there's non-equilibrium structures here and here, which cause compressive stresses. And compressive stresses actually are the rule rather than the exception in many different types of CVD deposits. Okay, well, if these stresses can be relieved by high temperature annealing. And so this is the magnitude of a 550 and 615 deposit and the 570 deposit. And then if you anneal these, what you see is 570, let's talk about first. Tensile stresses first increase if you anneal at 615. This increase is due to that last bit of uncrystallized material, the last 20% crystallizing by this post-deposition heat treatment. And then you begin to get some annealing. Likewise, 615 is compressive, and as you heat up, you get some annealing. These are conventional types of annealing processes that there's enough mass transport going on to allow these residual stresses to be relieved. The 550 material, when you heat it at 615, it all crystallizes, so it goes from a large tensile stress, large compressive stress to a large tensile stress, and then it too begins to anneal. So what's the big deal? Well, just anneal everything. Well, the big deal is there generally are strict thermal budgets, and if you try to make a transistor, you just have to be very careful of its structure, and you can't anneal at temperatures like this to get rid of these oftentimes annoying residual stresses. The result of that is MEMS designers do things completely backwards. The way they do things is they have to build the structure first and then the electronics afterwards. Oftentimes you would like to build the electronics first and then build the whatever structural sensor actuator you want to do on top of this, so it imposes very awkward design rules. And it would be nice if this kind of annealing didn't have to take place. Well, these are stress profiles of tensile stresses deposited samples done at a range of thicknesses, deposited at 570 and annealed to crystallize the silicon, and this for compressive stresses, you'll see that it takes a fair bit of deposition until you get a steady state. And in both cases, it's about 2 microns. It starts out that you have small residual stresses which increase to the steady state on the tensile side. Compressive stresses, the initial ones are large, and they decrease. And in addition to these stress evolution, all these films have through the thickness stress gradients. And that's much more significant. These measurements of stresses represent average stresses as a function of time, but there are stress gradients in both kinds of films. But we had the idea to do this experiment where maybe somebody could kill a bit of the lights. Is that, yeah, that's better, thank you. So here is the SiO2 sacrificial oxide in which we build the structure. And in this experiment, we deposited a thin layer, about 1/2 micron, at 570. And at this thickness, it remained amorphous during that brief heat deposition time. We then raised the temperature and went to 615. During the 615 deposition, the material at 570 crystallized. Okay, so far? And now a miracle happened. We then changed the temperature again back to 570, and I would have guessed that this columnar structure would have continued to grow because so many processes are dominated by nucleation issues, and having the columnar film available, you would have thought that you would avoid any further issues about nucleation. But that's not apparently the way it works. As I mentioned earlier, the kinetics of deposition are sufficiently rapid at this temperature that the atoms are not able to, by surface diffusion, when they get deposited from the vapor phase onto the pre-existing columnar silicon, move around until they find the correct equilibrium position to allow these columns to grow. And so this 570 film is amorphous and doesn't crystallize till you deposit this 615 and so on. And the final film was deposited at 570 and is then annealed at 615 to crystallize the last bit of material. And in principle, this gives a way to control the stresses in the film. And of course, I wouldn't be telling you about it if it didn't work. And so you can, depending on how careful you are, you can make the as-deposited stresses as close to 0 as you like. And these materials are pretty robust against further annealing. Now, there are many ways to add up positive and negative numbers to come to 0. That's the easy part. I mentioned earlier that there are stress gradients in each of these films. And so if you measure the stress gradients and then adjust and get to 0 in just the right way, you can make films which have 0 residual stresses overall and 0 residual stress gradients. And that's really neat. Because when you do that, well, let me just say one thing before I get to that. This columnar microstructure is rather rough on the scale we're talking about. This is the RMS roughness is 70 nanometers. And there was, when we were doing this work, a lot of interest in optical MEMS. That bubble burst with the .com failure. But at this roughness, materials are too rough for any optical MEMS devices. And so you have to go through a rather expensive planarization, and people would like to avoid it. Since you limit the extent of the columnar deposition by this alternating amorphous and crystalline material, we get the multi-poly surface has a much improved surface roughness. But what's really important about this process is, as far as we can tell, we can make arbitrarily large devices which are flatter than we can measure. So this is a micromachine strain gauge. As shown here, if there's compressive stresses in these four legs, these are the anchors. There's still some SiO2 pinning this to the surface. These are floating. And when you release this material, if there's a compressive stress in the film, you'll get the motion of these two verniers as indicated. And we think we can measure, just assuming a modest resolution, optical resolution of 1/4 micron, we can measure microstrains down to 8 by 10 to the 6. It's really quite a good device. The important point is here we have a suspended device. It's about 3/4 millimeter long. It's a very large device on the MEMS scale. And we have the radius of curvature of this device is larger than the best measuring tool we own. So we cannot measure whatever curvature there is in this device. It is flatter, as flat as we can measure. I'll show you how this works later on, but it's an indication that you can make large, flat MEMS devices, and for certain applications, such as an accelerometer, a large proof mass the larger the proof mass, the more accurate the accelerometer would be. There are other things you can do. You can, we have enough understanding of the stresses and stress gradients that if we want to design a stress gradient, we can do that. This was some attempt to make a mirror for an optical MEMS device designed to have 6 millimeter radius of curvature, and it's perfectly circular, as you can see by these interference rings. This is really a nifty technology, I believe. Okay, well, so I wanted to tell you about multi-poly. If any of you have need to make large, flat devices in the MEMS scale or devices with controlled curvature, we know how to do that, and we even have some patents that should protect us. But I've shown you a lot about tensile and compressive residual stresses. It would be nice if one could take a device and determine aspects of its mechanical behavior without having to build an ultra-small Instron testing machine or some other device like that at the microscale. Could we do it at the wafer level? And the answer is yes. MEMS types talk about clamp beam. So this is a beam for which it's anchored here and here. And the way we did this, we built devices with varying micromachine notches. These don't have sharp notch tips. They're rounded, but nevertheless, there's stress concentrations. And the way the measurement works, we build a device. We actually have a dozen or so of these beams with different notch depths. And we look to see which beams have fractured and which haven't. Those beams in which the stress concentration times the residual stress at the root of the notch is larger than the fracture strength will fail, and the shorter notches will not. And here's the device. So this is one beam, this is a second beam, and so on. This was a sample that had 318 megapascal tension as measured by our strain gauge. At this notch depth, the stress concentration at the root of the notch was too small to cause fracture. This one, it was large enough. And you can see these are our statistics. These are our notch depths. These are the calculated stresses. And this is the statistics. We made 14 devices. That's another thing about MEMS. You get statistics very, very easily. If you wanted to make 100 such devices and you want to spend some time at a microscope just seeing, getting better and better statistics, it's not hard to do. But you can see that in this device, all notches of this depth failed. No notches of this depth or smaller failed. And a subset of notches with this depth failed, and so we could determine the strength at 3.6 GPa. The strength, by the way, I should mention, is very sensitive to, it's a brittle material, silicon at room temperature, and like any other good ceramic, its strength depends entirely on the magnitude and severity and the number of defects at the surface, so-called Griffith flaws. And in this case, the defects which cause failure are the polysilicon reacting with the plasma etch. You don't get a perfectly smooth surface, and you can actually calculate what the notch, the defects that cause failure, as I'll show you that a bit later. Well, there are some designers who'd like to build in compressive residual stresses in their devices, and there's a way to measure strength, tensile strength, even in devices with compressive residual stresses. Some of us like to use something called the diametral compression test. And typically, a device like this would be about 1 centimeter in diameter and about 1 millimeter thick. It's very easy to do because brittle materials like ceramics or silicon, it's very hard to get well-aligned tensile grips. With metals, it's easier, a little bit of deformation in the grips, and you're at the first little bit of loading and you're okay. But brittle materials, if you try to do tension, more often than not, they'll break right in the grips. And so ceramists want to have some way to use a compressive loading, and this device allows that. When you load up in compression, you get tensile stresses in this central part of the beam, and this is a very useful device. Here's the MEMS equivalent. And again, when you release a structure containing compressive stresses, there'll be tensile stresses in this particular part of the device. And here is our examples. This is it's anchored here at this notch depth. This is a 300 megapascals compression. At this notch depth, the tensile strength of the film was not exceeded, no failure. Here, the failure did occur. This is our statistics. The strength is a little less than in compression, and the reason is because you remember well, I'll just show you, don't have to remember. This I didn't show you the roughness, but 570 material is much smoother because it's this amorphous material that crystallizes. It's much smoother than when you get to this compressive material, and the difference between 3.1 and 3.6 GPa is just the difference in surface roughness between these two deposition temperatures. Well, I've talked about strength, but anyone who takes Professor Lewandowski's class will learn that it's fracture toughness rather than fracture strength, which is really important in determining the performance of a brittle material. And to do that, you have to do some sensible fracture mechanics testing, and we can do that as well. So this is the same stuff I've told you before. But now what we do is, after we get to this stage, we actually put a Vickers indent, not in the device, but in the sacrificial oxide. And it's an overloaded Vickers indent such that there's cracks coming out of the corners. And these cracks propagate, and they propagate right up into the device. And then what we do is, prior to release, we measure the crack length. And then we release the structure and look to see which devices failed and which didn't. That will be clear in the next slide. Or I should mention, we almost always use critical point CO2 drying to make sure there are no capillarity stresses. The thing you desperately don't ever want to have in a MEMS device is have your floating device touch a substrate. It causes something called stiction, which is the end of the game. If any of your devices ever touch, it's over. So you really need to be very careful about capillarity-induced stresses at this stage of the process. So here's the schematic of the device. It's what I told you. It's this clamp beam. This is the oxide that's still anchoring the beam. Here's our test specimen. Here's the indent. There's a crack, and it ran through and into the material. It's actually it's very hard in mechanics to do fixed grip testing. It's very easy to calculate stresses and other aspects of mechanics using fixed grip conditions. It's hard to achieve them in practice. In this MEMS case, this is a perfect example of a fixed grips fracture mechanics specimen. And so you can calculate what the stress intensity factor K1 is in this device, and then look to see which device has failed upon release and which didn't, and therefore you get this critical value of K1C. Here is the device itself. It's a tensile bar. The indent is put in here, and this is the edge of the indent. This is still the sacrificial oxide. This is our device. It's here. This white feature is just some charging from the edge of the silicon tensile beam, and you measure this crack length, this distance, in the SEM before you crystallize. Fortunately, many of you will have visited our Swagelok Center for Surface Analysis of Materials, and we've got lots of SEMs to allow this kind of work to be done. Here is our data. So we've done 3 different devices, 3 different wafers with these levels of residual tensile stress. These solid lines are calculated stress intensity factors for different crack lengths. The fact that they go through a maximum and then decreases just has to do with what happens to the stresses in this beam as this crack grows. That's a finite element calculation. And the blue symbols are devices that didn't fail, and the red ones fail. And this is what we take the fracture toughness, K1C, is upon release in aqueous HF solution. It'd be very hard to get this measurement with this precision in any other way. It's interesting that there was one device of this length that didn't propagate to failure, and it's pretty clear that this crack propagated and then arrested as K fell below K1C, which is just what you'd expect in a fixed grip test. Okay. The last of these things has to do with galvanic corrosion or anodic oxidation. We had got into an interesting dispute with a colleague at Berkeley on fatigue of polysilicon, and I think the community got a great deal of pleasure out of watching these 2 warhorses, me and my pal at Berkeley, whose name I don't have to mention here, duke it out. I think we won. Here's the issue. At Berkeley, although there's a pretty good fab, they didn't use their fab. They sent their devices out to be manufactured at a fab in North Carolina, practicing what's called a multi-user MEMS process, MUMPS. And we made devices in our clean room across the way. And this is a cross-section of one of our devices, which had been released for 12 minutes in HF. And you may wonder why I show this micrograph, because there's not much to see, and you'd be right, there's not much to see. There is a very thin passive native oxide about 20 angstroms, and that's just what people expect to be on silicon released in HF. It's well known in the device industry and so on. Here is a sample we got from another collaborator, and there's some wretched-looking stuff at the top of this device which looks fuzzy. And when you do XPS analysis, again down in Glennon 110, what we find is this is the oxygen profile as we spread it away down to a depth of about 40 angstroms. There's some carbon here, but there's carbon on everything, so-called adventitious carbon. And this, you can see that there's a native oxide of about 20 angstroms. That's just about what everybody expects. On this MEMS sample, it's something quite different. Notice the scale. This is 40, 80, 120 nanometers, not angstroms, 1,200 angstroms. There's a very thick surface oxide. And you can see it's this wretched-looking stuff on the top of this piece of silicon. This silicon hasn't passivated. Very, very strange. No one has ever considered non-passivating silicon. Everybody knows, including all the MEMS engineers, that silicon just forms a native oxide, and that's the end of the story. Well, it's not the end of the story. So Joe Pear and I and Hal Kahn, a graduate student, set up this experiment. This is typical electrochemical experiment. There is HF solution, a gold cathode, a conducting silicon, a doped silicon anode, and just a salt bridge to a reference electrode. And lo and behold, there is some significant current flowing, a galvanic corrosion of this magnitude. Although silicon itself is immune to corrosion in HF, and gold itself is immune in HF, when you make an electrochemical couple, you get some current flow. And the origin of this can be seen in this, what's called cyclic polarization curves. I won't, if you're not an electrochemist or a corrosion engineer, you might not be familiar with these, but all this is you apply a potential and measure the current flow, and you can learn a good deal about the electrochemical dissolution of materials by the particular form of the cyclic polarization curve. The important point about this slide is that when you have pure silicon, that's the value of its open circuit potential. But when you have gold on silicon, you get it becomes more cathodic by about 200 millivolts. And that results in this kind of current flow. And a number of years ago, there was great excitement in the semiconductor world to try to make porous silicon devices. And the reason people are interested in porous silicon, silicon has an indirect band gap, and therefore it can't be used for LEDs or other things like that. And sort of the holy grail of optoelectronics has been to make a silicon-based laser or a silicon-based LED. And there are enough surface steps, surface sites on porous silicon that there was hope that you could get a direct conversion of electrons into photons. During that work, folks discovered that you could produce porous silicon electrochemically, and if you did that by working in this current range, and that's just the range that is occurring when we make this galvanic couple in an electrochemical cell. So what's happening when you release, oh, and I should say that the standard process steps, these standard process step, in the MEMS process, the very last step prior to release is to put gold contact pads on. Electrical engineers need to make electrical contact with their device. What better thing to use than gold? Gold has been used forever for ICs and transistors, so naturally they put gold on there. And naturally, they've now gotten to a regime where silicon is no longer passivating. And we studied this in the TEM. This is a cross-section. This was the actual sample we used in this electrochemical experiment. And there's been some corrosion in the top half of this 2-micron thick film. We've done some more fancy electron microscopy, the so-called energy filtered TEM. The important thing is this is just an image, just an ordinary image. The details aren't important, but you get silicon-rich and oxygen-rich regions. What's happening is that the release step causes a porous silicon to be formed, and it does form a thin native oxide, but there's so much surface area of porous silicon that you get something which looks like a silica, non-passivating silicon, and appears to grow, there's so much porous silicon present. So, caution, gold contacts may be dangerous to the health of your device. Okay, well, we also are interested in active devices, and this is where I would say MEMS allows folk like me to do experiments which wouldn't be possible by conventional means. So this is the same kind of technology I told you about earlier, except we show here that we need to have conducting silicon, semiconducting silicon, to do electrostatic actuation. I'll show you that in the next device. And you can do it either by, at this stage in device preparation, heated in a boron-containing source as the way you make transistors, or most of our devices, it was simpler to just sputter deposit a very thin film of palladium, and that allowed the device to be sufficiently conducting. And this is the type of device. We use the same sort of interdigitating comb fingers that are used in the accelerometer in your car. This is when you apply voltage to between these black and gray regions, this device will move downwards as shown here, and then this is our fracture mechanics sample. This is a close-up. Actually, it was a significant development challenge to make these devices, which had these 1,438 pairs of comb fingers. If you're not calibrated, 0.8 of a millinewton may not seem like a large force, but it's a very large force at the microscale or nanoscale. And this is, we measure the movement using this vernier and calculate the actual stresses by finite element analysis. And the important thing I show in these two devices, this is mostly the device we use, which would just create a tensile stress at this region of this micromachine notch. But we can turn this upside down, and this allows us to okay, so how do we work this device? We put this device in resonance, and its resonant frequency is about 10 kilohertz. And then we simply increase the amplitude of the AC voltage until we get failure if we wanted to do a DC, a short-term test. But if we combine a DC bias as well as the AC alternating voltage, we can do experiments with mean stresses. And that turns out to be very useful in the experiment I'm going to show you. Again, essentially it would be impossible to do an experiment on a brittle material like silicon with both mean stresses and alternating stresses, but DC and AC biases make this relatively straightforward. What people who do fatigue like to measure is SN curves. SN simply means the stress of the alternating cycles times the cycles to failure. And this is, as far as I know, the first SN curves that we produced was Kahn, Ballerini, Mullen, and myself in a quite prestigious journal. And you can see that there's some noise here. It's not, but these were early experiments. But it's very clear that the short-term strength of this batch of silicon was about 5 megapascals, And by the time you got out to a stress of 2.5 GPa, the cycles to failure were 10 to the 9th. And by the way, this is in the regime what's called very high cycle fatigue. And again, it would be very hard to do this in a conventional Instron machine. Graduate students would be grandfathers before they finished their PhDs if they had to wait for 10 to the 9th cycles. These tests, by the way, were done without any mean stress. These are just, for those of you who are not familiar with this jargon, R-1 simply means that the magnitude of the tensile and compressive stresses were equal. If you have tensile 0, that would be R0 and so on. But we had equal compressive. And we assume, of course, that failure occurred brittle material on the tensile part of the cycle. And to understand why what was causing failure at the lower stresses at the longer times. So we resorted to a ceramic trick. This has been well known mostly in the glass field. When you look at a fracture surface, what you invariably find for brittle material is that there's a failure point somewhere here, and then there's a region where you get a very flat fracture surface. That's called a fracture mirror. And there's a well-established relation between the size of the floor and the size of the fracture mirror. Essentially, the size of the fracture mirror relates to where the crack velocity gets to where the speed of sound. And then the crack is still accelerating, and you get very rough because you get subsidiary fractures ahead of the main fracture. But you can see that at high stresses, there was a much smaller fracture mirror, and therefore a smaller fracture origin, than at lower stresses where there's a larger mirror. And so the implication, very clearly, is that there's some flaw, and it's growing subcritically. It's growing that the flaw itself present is not large, not severe enough to cause fracture at this stress, and you have to wait until the flaw grows. There's an inverse relationship between the fracture strength and the size of the flaw. The larger the flaw, the smaller the strength. So there must be some mechanical damage. And it's peculiar because this kind of behavior is well known in oxide ceramics or in oxide glasses, where it's very clear that you get subcritical crack growth due to a form of stress corrosion, that a crack in the presence of water vapor, which is almost always around us, can fail subcritically, and the crack will slowly grow due to this kind of stress corrosion cracking. But silicon is immune to this kind of thing. As far as we know, there's no evidence that the strength of silicon is sensitive to the presence of moisture, either liquid water or atmospheric moisture. Very different from oxide ceramics and oxide glasses. Well, there's more to cyclic fatigue than just SN curves. I'm going to show you evidence for both, further evidence for mechanical damage during these compressive cycles, as well as some unusual grain boundary plasticity. So what we're able to do with our devices is impose mean stresses of varying sign and magnitude. And remember, when this is our data, the way we do this experiment is we impose a mean stress, and then we increase the amplitude of the AC voltage until we get failure. So we impose a DC bias, and then we assume that failure occurred at the maximum of the tensile part of the stress. And when we compare this with monotonic loading, that's the value of the monotonic stress, about 4 GPa, and you see there's a dramatic weakening with large negative mean stresses. And our interpretation is that there must be asperities on the sample surface, and we're driving two asperities together, causing some mechanical damage. And this is not sensitive to environment. Shown some experiments in air and in 10 pascals pressure. And contrary to lots of people's intuition, compressive stresses can be very damaging. We normally think compressive stresses in brittle materials are good because they fail under tension. This is an example. This is high cycle fatigue with mean stresses where it's not so good. We did another kind of experiment, which was also interesting. And this experiment involved, again, there's a monotonic strength. This was a little weaker batch, rougher surface. What we did is we cycled for 6 million cycles at some value of the mean stress, then unloaded and loaded to failure. And at small values of the mean stress, we saw no effect. But at large compressive mean stresses or large tensile mean stresses, oh, and by the way, we fixed this delta sigma at 2 GPa. At large values of the mean stress, we got strengthening. There must be some form of plasticity. And we know that there's almost no example of plasticity in silicon until you get to temperatures of about 600, 700, 800 degrees. And the next two slides are speculative, but there's been some recent calculations by a very well-known theorist, Adrian Sutton, who showed, and the details of his calculations aren't important, who showed that when you make silicon grain boundaries of any misorientation, from zero, over the whole range of misorientations, that the boundaries are not just an amorphous melange, but that they're structured. And the structures, there are these A units and B units, which refer to specific arrangements of silicon atoms in the grain boundaries. And these, the proportions of A to B change with misorientation. And it's entirely possible for very small motions of atoms in the grain boundaries to cause an A unit to irreversibly transform into a B unit. And if that happens, that is effectively a form of grain boundary plasticity. Any plastic deformation causes a small change in shape, and if you change A units to B units, that's what you get. We suggest that this must be the origin of what we've observed. I see my time is up. I'm going to, I was too ambitious. Let me just summarize. I've told you a few things of various aspects of residual stress in electrochemistry. I think material scientists have made and can continue to make important contributions. And I've told you about this mechanical damage during high cycle fatigue. I didn't tell you about items 2 and 3. Very interesting, but if any of you are interested, we can talk offline. Thank you very much.
Can you make your layered structure alternating between the 550 and 650?
Yep.
When you put down a layer in anneal at 615, why doesn't the previous layer that was anneal at 550 see that and continue to change structure?
Temperatures are too low to do anything but crystallize. In order to, I didn't show you, but when you anneal to 1000 C, you essentially wipe out that layer structure by grain growth. But at these low temperatures at which we're doing the deposition, the only thing that can happen is either you get crystalline growth or amorphous material that crystallizes. There's no other microstructural changes possible at these low relatively low temperatures for silicon. Yes?
I have a very simple-minded question. And that is,
Those are always the toughest.
I looked at those multi-folding depositions, right? And it struck me that the depth or the height of the different layers was different. And in my mind, this is so because you adjust the height of the get a zero overall residual stress.
That's half of it, but what's more important is that you need to adjust the thickness to get residual stress gradients also to balance out. Because you can add to plus and minus to zero many, many ways. But those are designed to add to zero plus to give zero residual stress gradient. Because the gradients, we had to measure those, we have measured those, and that's really an elegant processing step, I think.
And the other simple-minded question is, those are average values.
Yes?
And so if one would dare to actually get a distribution, to which extent the distribution is very much around that average?
Well, what I didn't have time to say, there's something else. It turns out, and any mechanics person knows this, that you can, if you're far from the neutral axis of a device, then a small tensile or compressive stress can cause a relatively small displacement can give you, relatively small thickness can give you a large displacement. So we've had the occasion where we've made wafers and we took one and processed it and realized we didn't do it correctly. And we could then put the device back into the deposition chamber and add a small additional correcting layer and bring everything into whatever the desired thing was. So it's a very, very nice effect, consequence of this kind of building a multi-layer, that even if you haven't got it quite correctly the first time, you can just correct it by a very small additional layer, 1/10 of a micron or so, which people won't care about. But if you have a curvature like this, you can cause it to go flat by a relatively thin correcting layer.